Assalamu alaikum warahmatullahi wabarakatuh. Today we're going to speak about the ultrafiltration membrane for pharmaceutical removals from wastewater. As you may know, the wastewater industry these days is a major challenge due to the major hike, the recent hike in the general technology of the recent industry hike in technology. Our main challenges in the recent years is the wastewater treatment industry, due to the fact that many industries have had an epic hike in the technology itself. So, in order to overcome the one of these aspects, the major aspects in the wastewater industry, we decided to overcome this by using a membrane-based separation technology. This technology is called the ultrafiltration membrane. Advantages due to the fact that it's very selective in removal of the pharmaceuticals and other micropollutants. It has a very low operating pressure compared to nanofiltration and reverse osmosis. It has a higher flux rates and throughout compared to tighter membranes. In addition, it has a minimal chemical usage compared to conventional treatments, other conventional treatments. The main aim of the study was to develop, design, and fabricate 4 different configurations of ultrafiltration membranes. The different configurations were supported and unsupported, and with or without silver nanoparticles technology. Furthermore, we were gonna evaluate the membrane efficiency in removing the pharmaceutical waste. Example, we chose azithromycin as an example due to the fact that it's a wide broad antibiotic, which is used in the pharmaceuticals industry, and it's also used mainly in, it will be found in the wastewater pollutant, as a pollutant. Finally, we're gonna evaluate the membrane efficiency of the 4 different configurations. And we're gonna correlate that to the physical properties of each membrane. The first step is the membrane fabrications. The 4 major materials used were PES, the polynitrate, and PEG. The PES is the primary polymer, the PVC is a support polymer, the silver nitrate is an antimicrobial agent, and the PEG was the pore former. In this process, we will use the phase inversion technique. The whole idea lies in the fact that we put the PES with NAP solution in methyl pyridine, as it will dissolve in this solution. Furthermore, we're going to apply it on a support sheet. Furthermore, after that, we're going to use the PVC as a support polymer. And then we're going to dip it in a cold water solution. What will happen when we add the sheet with the membrane in the cold water? The NMP is miscible in water. So what will happen? The NMP will move from the polymer, and the water will come instead. It will replace it on the surface sheet of the polymer. So what will happen by that? We will have a porous structure of the membrane. In addition to that, we can add also in the first step the silver nanoparticles. And we can add the PEG, the pore former, as it will enhance the structure of the pores on the membrane surface. So, as a final result, the membrane will contain PVC 13%, PEG 3%, and NP 84%. If there's no silver nanoparticles, if there's silver particles, it will have the 1%, and the NMP will be 83%. Furthermore, the materials and methods. Okay, we will cover in this aspects the fabrication of UF membrane. I already mentioned that chemical reagents, experimental setup, fabrication of sample solution, filtration of membrane experiment, assessing the physical properties of the membrane, and finally testing the UF membrane efficiency and the removal of this. As I mentioned earlier, the steps I mentioned theoretically 3 seconds ago, now these are the actual solution. This was conducted with the help of Dr. Marwa Shalabi in the National Institute point, along with my professor, Dr. Mustafa Salim, from Alexandria. As I mentioned earlier, we add all the polymers, the early polymers on the sheet, and then we roll it, casting it, and then we put it in the cold water, thus making it solidified. And the final step, we will wash it with the distilled water. And this is a description of the phase inversion technique. Okay, now we go to the experimental part. The major chemical agents used in this experiment was potassium permanganate and potassium carbonate and azithromycin as our source pollutant. Further, we have the experimental setup. Here, the experimental a very conventional filtration system. However, we added a rotary pump, thus facilitating the filtration process in an easy and consistent manner. The set of components are flask containing wastewater core. We have stainless steel membrane holder, in which we will put inside the part of the membrane to be tested. We have a cylinder permeate acquisition system, flow control valve to control the flow of the valve, and we have a strain gauge manometer to sustain the pressure at 1.5 bar during our filtration experiment process. These are the rotary pump utilized experiments. Furthermore, we tried as our best to mimic a real sample as a pharmaceutical waste from a pharmaceutical factory. Physical properties of tested membranes. The are follows. We have, as mentioned earlier, the superiority for M1, and also the OCA is very the best among them. It has the best hydrophilicity ability compared to the other three. We have the surface roughness also with the least, and also the structure of it was finger-like. It was the best structure and coarse structure in terms of the in compared to the other foam membranes. So as mentioned earlier, in relation to what I mentioned earlier, we have the flux analysis over time. As you can see here, the M1 shows the least flux as a start. However, it showed by the rest of the experiment, it was stable, not like the other three. The other three started with a very high flux, and then as the experiment progressed, it reduces tremendously, and the fouling happens faster than the best one, other than the N1. It shows similar patterns for the acidic and for the basic medium. As you can see here, we calculated the efficiency with relation to the chemical oxygen demand. Why? Because the azithromycin contribute to the organic content of the wastewater. So in order to find a direct correlation between the COD and the azithromycin, we chose COD as a major. We chose the COD as the major component as it has a direct proportion relation to the azithromycin. If we were looking at the table here, we find that the efficiency for the acidic was superior by 93.2%. And for the basic medium, it was 69.52. And you can see here that the acidic has a higher performance than the basic due to the fact that the lower the pH, the slower that the scales will accumulate over the membrane surface. So that's why in the basic medium, the efficiency was 69.6. Finally, the summary and conclusion of K findings. We find that the M1 was superior with 93.26 COD rejection and contact angle 75.5. And for the basic 69.52 and the surface roughness was 0.5 micron. So as a final result, the M1 was the best, which was supported and contained the silver nanopore technology or nanoparticles on it. And these are my references. That's all. Many thanks to all of you.